Greetings everyone. So in this video, we're gonna explore the foundational concepts of linear algebra that are essential for data science and machine learning. Whether you're training a neural network or performing dimensionality reduction or just working with data sets, linear algebra is everywhere. But don't worry, we are not diving into the dry theory or heavy math. Instead, I will try my best to walk you through the core ideas as intuitively and visually as possible so you can actually understand how these concepts power real world machine learning models and tools. So these are the topics which we're gonna discuss in the video.
Let's see what are scalars. Scalars are nothing but a single numerical value. It has magnitude, which is a value, but no direction. So let's take example of temperature in your room. Let's say it's cold, like 17 degrees Celsius, but you don't care about the direction of heat or direction of temperature, but it's just a value. So that's what scalars are. It can be any value like x equal to zero point 0.4 or any value, but it only represents the magnitude, which is the value, but not any direction. So these are used in machine learning for various purposes, like for example, to represent the accuracy of a model or to represent the loss of a model or something. Now let's see what vectors are. We saw that scalars represent only magnitude, which is the value, but vectors represent both the magnitude and the direction, and it's one dimensional. So let's take an example of a coordinate system in a 2D plane, let's say 2 comma 4. This is 2 comma 4. So these are the set of ordered values which not only represent the value but also represents the direction of where the point is present. So this is called like a vector point in this 2D plane. So this is also used in machine learning, like there is a thing called feature vector. So let's say we're going to identify a person with respect to these features, height, weight, and age. So these are represented as vector values. Let's say height is 175 centimeter, weight is 69 kgs, and age is 21. So this is a vector. And vectors are used everywhere. As you can see, even the color values here, the green color is also represented by a vector like RGB values. We have a set of RGB values which represent this green color. So these are called vectors. Now let's see what a matrix is. Matrix is nothing but a rectangular array of numbers arranged in rows and columns like this. So let's take an example of a data set used in the machine learning. We have the name, height, weight, age, and the people and their metrics. So this can be represented as a matrix like in given in here. So also let's take an example of a grayscale image. So this grayscale image has numerous number of pixels. So the pixel values are ranging from black to white, so this also can be represented as a matrix here. Now let's see what a tensor is. Tensor is an array of numbers that can represent data in multiple dimensions. So we saw matrix. Matrix represents two-dimensional data, which is rows and columns, but tensor is a generalized form through which we can represent vectors, scalars, matrix, and any dimensional data in form of a tensor. So typically a scalar would be a zero-dimensional tensor and a vector would be a single dimension, which is just a list of numbers, and the matrix would be a two-dimensional tensor, which is rows and columns and so on. So let's take an example of RGB image. So each pixel in this image will have a red, green, and blue values, and this image has a height and a width. So the image can be represented as height and width of the pixels and the channels, the RGB values. So this is technically a three-dimensional vector or a tensor. Let's see some concepts in vectors. What is a vector? Vector is a ordered set of list of numbers. So there are two types, column vector and row vector. So column vector, it has only single column and multiple rows. So here the shape of the vector here is 3:1, where 3 represents the number of rows and 1 represents the number of columns. So similarly, row vector has only a single row and it has values across multiple columns. So the shape here is 1:3. So 1 is the number of rows and 3 is the number of columns. So the values which are present inside the vectors are called components, which is 2, 5, and -3. And the number of values which a particular vector has, it's the dimension of the vector. So here it has 3 values, so the dimension is 3. So let's say example of a colored pixel value or GB value, and these have individual numbers, and these are called as components of this vector. So let's talk about vector addition. So let's take example of these two vectors A and B. So these are nothing but points in a coordinate system. So here we can see I plotted the A and B vector, which is 1, 3 and 2, 1. So performing addition or subtraction, we have to keep in mind an important thing that the vectors which we add or subtract, they must have same dimensions, or we can say they must have the same number of components. Here we can see these two vectors have two components each, and which is 1, 3 and 2, 1. The way we add is we just add the corresponding components. So just 1 and 2, 1 plus 2 is 3, and 3 plus 1 is 4. So this is the added final vector. So let me plot this in this graph. So 3, 4, and you can see this is the new added vector. So what I'm gonna do is uh, I'm gonna translate this B vector. Translate means just shifting it above or below without changing the direction or magnitude. So I'm gonna place it on top of the head of A vector. So just a minute, I will place this here. Yeah, so this is B vector now. So I just shifted or translated this B vector from here to here. So you can actually see that the head of the B vector, which is 2, 1, which is actually coincided with the new resultant added vector. So you can see the visual effect. So like let's say we are moving from path origin to A and to B, and the sum of the total vector and the magnitude we can see it through the resultant vector. Also we can see the direction of the resultant vector due to the addition of these two vectors. So let's talk about vector subtraction. Vector subtraction is similar to addition. So let's say we are subtracting A minus B, and this can be written as vector A added by the negative value of B vector. So in 2D plane, the negative value represents the opposite direction. So let's draw the opposite direction vector of B. So 2, 1 means it's minus 2, minus 1. So it's here. So this is basically minus B. So the way we subtract is similar way. We just subtract the corresponding values or components. So 1 minus 2 is minus 1, and 3 minus 1 is 2. So this is the resultant vector, minus 1, 2. Let us draw this in the plane. So minus 1, 2. Yeah. So this is the resultant vector. So to visualize this, we can translate this negative b upward. So it's gonna be like this, and this is how you can visualize the vector subtraction, and this is minus b, and that's how you do the vector subtraction. Now let's talk about vector multiplication by a scalar. Let's take this vector 2, 1 and multiply it with the scalar value of 2. So how multiplication works is we just gonna multiply the corresponding components of the vector. So it becomes 4, 2. This is the new vector. Let me quickly plot this in the graph. So here we have 4, 2. You can see that here the vector has gained new magnitude, which is doubled in size, but it doesn't change the direction. So whenever we multiply a vector by a scalar, the magnitude of the vector increases or decreases by a value proportion to the value of the scalar, which is 2 here. That's why it doubled in size. Let's take another example where instead of multiplying by 2, we multiply it with 0.5. So in that case, this becomes 1, 0.5. When we plot this in the graph, you can see that the vector has reduced in size, but the direction remains same. So let's multiply it with another value. Let's say minus 1. What happens in this case? It becomes minus 2, minus 1. So in this case, the direction is reversed. So it's in this direction. But the direction value angle doesn't change. So it remains on the same line. So whenever we multiply a vector by a scalar, the magnitude alone changes and the direction is on the same line or reverse, but the angle of the direction doesn't change. Let's talk about vector multiplication, which is dot product. So there are two types of products, cross and dot products. We're going to look at dot product here. So let's take two vectors, a and b, 3, 4 and 2, 1. So in order to do a dot product, they must have the same dimensions or same number of values. So how we going to do this? We just going to multiply the corresponding components and add them together. So 3 into 2 is 6 and 4 into 1 is 4 and we get 10. So output of a dot product is always a single value or scalar. So to understand this more, we're going to look at another equation of the dot product. So here, so what it says is the dot product of two vectors is nothing but the magnitude of vector A multiplied by the magnitude of vector B multiplied by the cos of the angle between them. So what do you mean by the magnitude of vector, which is represented by two bars, which is nothing but the length of the vector A. So how we can find this? This is nothing but a vector in a 2D plane. So we can find this with Pythagoras theorem. So this length is 4 and this length is 3. So we can find the length of this diagonal with Pythagoras theorem, square root of 3 square plus 4 square. And similarly, we can find the magnitude of vector B also. So magnitude of vector A is 3 square plus 4 square square root, which is 5. And similarly, for the vector B, we have magnitude nearly 2.236. So if we plug these values in this equation, we can actually find the angle between them, which is approximately 26.57 degree. So what does the dot product mean? So to understand this, let's look at the cos values here. So what is cos 0? Cos 0 is 1 and cos 90. Cos 90 is 0 and cos 180 is minus 1. So let's say the vector A is going in the same direction as vector B and we don't have the vector here. We have it in the same direction of vector B. So what is the angle between them? The angle between them is 0. So what is cos 0? Cos 0 is 1. So we will have a positive value for the dot product. Let's say the vectors are perpendicular to each other instead of moving in the same direction. So instead of now overlapping with the B vector, it is perpendicular 90 degree. So what is cos 90? Cos 90 is 0. So the whole dot product will be 0. So instead of 90, let's say they are completely opposite to each other, minus 1. So this is cos value is 0 and this cos value is 1. So if they are completely each other, they are 180 degree apart from each other and the cos value of it is minus 1. So the dot product will be negative or minus 1. So what it explains? It explains how the direction of one vector is with respect to the direction of the other vector, how it moves in the direction of the other vector. So the direction of one vector with respect to other vectors indicated by the dot product. So with respect to the cost values. So let's say if there are perpendicular to each other, it slowly becomes 0. So the dot product will be 0, which represents that they are perpendicular to each other. And when it starts to become negative, which is on this part, they are completely opposite to each other. So we can see they are completely moving in different directions. So at this point, the dot product will be negative because the cos value will be starting to become negative. Let's talk about cosine similarity and orthogonal vectors. So by this equation, you're familiar with the cos theta value. So by calculating the cos theta value from this equation represents the cosine similarity. So if the cos theta value, let's say the vectors are completely coinciding with each other and they are in the same direction, in that case, the cos theta value will be 1 because the angle between them is 0. So which explains that the vector is completely similar to the other vector. So in the other case, if it is in complete opposite direction, so let's say in this, it's just 180-degree, and the cos theta value will be -1. So in that case, it is completely not similar to each other. So this cosine similarity concept is used in various places like in NLP or recommendation system to find similar entities and to push that in recommendation system, for example, and so on. So next thing we're going to see is orthogonal vectors, which is nothing but when a vector and another vector have an angle of 90-degree between them, which means that they are projected orthogonally. Let's talk about L2 norm. So let's take a vector here 3, 4. L2 norm is nothing but the Euclidean distance which we calculated before. So L2 norm is represented by this notation. We have 2 bars and 2 below it. So which is nothing but square root of 3 square plus 4 square, which is square root of 25 is equal to 5. So let's see how to find the L1 norm of this vector, which is 3, 4. In previous L2 norm, we found out the Euclidean distance by the Pythagoras theorem. But now we're going to calculate the Manhattan distance. So Manhattan distance is also called L1 norm. So here the point is 3, 4 and the vector is 3, 4. So to find the Manhattan distance, we're going to add the x and y axis together, which is 3 and 4. So mathematically, we're going to add the absolute value of the x and y coordinates, which gives the Manhattan distance. So this is actually represented as the distance which we travel and cover. Let's say we are in a taxi moving from this point to this point, and we take this whole path 3, and we take this whole path 4, and total distance is 7. This is called the Manhattan distance. Let's talk about LP norm. We've seen L1 and L2 norm. So this is a generalized LP form. This is the equation. So let's take the vector 2, 2, and in order to find the L2 norm, which is represented as like this, we're gonna put 2 here. So instead of P, we're gonna put 2. That is the value of the norm which we're gonna find. So let's say index 2 root, and this summation and this xi represents the vector which we are using. The summation represents that we're just going to add all the components. So n represents the number of components or dimension. There are 2 here, so we're just going to add them, and we're going to take the absolute value, and we are raising them to the power of p, which is 2 here. So if we do that, we will get absolute value of 2 square plus absolute value of 2 square. So we will get that as 2 root 2. So 2 root 2 is nothing but the L2 norm, which is nothing but Euclidean distance. This is 2, this is 2. If you put the Pythagoras theorem, this is 2 root 2. So we got that, yes. So now we're gonna try to find the L1 norm. So in order to find the L1 norm, we're gonna put the value of P as 1 here. So if we do that, we will typically get the Manhattan distance. So let's try the L1 norm. So index 1 root, which is nothing, and we're gonna just add 2, absolute value of 2 plus 2. P is 1, so we don't need to mention that, and we will get 4. So 4 is nothing but the Manhattan distance. So this is 2, this is 2. So LP norm is a generalized way to measure the length or size of a vector in different ways depending on the value of P. So if the value of P is 1, it's L1 norm, or 2, it's L2 norm, and so on. So let's do something here. We're gonna find set of all vectors which have L1 norm value as 1. So what is L1 norm? The Manhattan distance, which is nothing but the absolute value of the components of the vector must add to 1. Let's say this x and y components. So we can easily find 4 points here which satisfy the condition. So this is 0 comma 1, so 0 plus 1 is 1, and similarly we find all the points. So we're going to find the rest of the points here which add to 1. So if we solve this equation, we can find some other points like a point here which is 0.1 towards the x side and 0.9 in the y-axis, and similarly a point here where it's 0.75 in x-axis and 0.25 in y-axis. These values add to 1. So similarly, if you find all the points and if we join them with a line, we will get a tilted square. We'll get a tilted square like this. So similarly, let's do for a L2 norm. So we're going to find set of all vectors which have L2 norm as 1. So this can be represented as an equation of a circle. So x square plus y square equal to 1. So it is nothing but a unit circle with the origin as a center and with the radius 1. So every point on this circumference will satisfy the equation and thus satisfy the L2 norm. So what if we increase the value of P here? Let's say for L3 or L4 or something, L3. So in that case, we will have a shape which is in between circle and square. Let's say a square or circle with the corners more curved. So eventually, if we increase the p-value up to infinity, we will have a perfect square shape. So you'll have this perfect square shape, and this represents that the perfect square shape which we get while putting the p-value to infinity. It is also called as max norm. So this measures the maximum absolute value of components in the vector. So this is particularly important in many cases, like it focuses on the dominant component. So the L infinity does only care about the largest coordinate, and it can be used in many cases due to this property. Like you can use it when to minimize or maximize a loss in a function or any fast computations. So for any fast computations, you just need to take the maximum value. So in those cases, you can use this. Want to see about matrices. Matrices are nothing but a two-dimensional array of elements arranged in rows and columns format like this. So A is a matrix and it has rows and columns, and similarly we have B. So what is the shape of this matrix? The shape of the matrix is represented by the number of rows into or by number of columns. So we have 2 rows here, so 2 by and 3 columns here, so 3. So shape of the matrix A is 2 by 3, and the shape of the matrix B similarly is 2 by 2 because it has 2 rows and 2 columns, and the individual numbers present in the matrix or elements, these are called entries or elements of the matrix. So next we're going to see different types of matrices. So before going into the types of matrices, let's see how to denote each element in a matrix. So let's take this matrix, let's name it as A. So it has 2 rows and 2 columns, so it is 2 by 2 matrix. So the first element 2 is in the first position, which is first row and first column. So let's say this position is 1 comma 1, where 1 denotes the row in which it is present, and the next one denotes what column it is present. So similarly for the element 7, what position it is present in. So it's in first row and second column. Similarly, this one is present in second row, first column, and this tree is present in second row, second column. So to mention this element 3, we will have this notation, the matrix name, and subscript we'll have the position, let's say 2, 2. So what do you have in second row and second column? The 3, element 3. So similarly, if you want to mention the element 1, you will have a subscript as 2, 1. So yeah, that's how we mention the elements of a matrix. And let's see what a square matrix is. A square matrix is nothing but a matrix where the number of rows equal to the number of columns. So here it is in the form of 2 by 2, 2 rows and 2 columns, and they form a square, so like all sides are equal, so that's why it's called a square matrix. Let's see zero matrix. Zero matrix is a matrix where every element of the matrix is 0, and we have identity matrix where the main diagonal elements are alone 1 and rest elements are 0. So what do you mean by main diagonal? The diagonal from top left to bottom right. This is called the main diagonal. These are 1. So what's the significance of this? So this can be used as 1 in matrix operations. So let's say in normal numeric operations, we have 1 into 5 into 1 equal to 5. So this one acts as identity matrix. So identity matrix acts as 1 in case of like matrix operations. So let's see a 3 by 3 identity matrix. So it will have 3 rows and 3 columns, and the main diagonal element will be 1, and rest elements will be the 0. This is the identity matrix for 3 by 3. So let's see diagonal matrix. So the diagonal matrix, only the main diagonal elements will be present. They need not to be compulsorily 1. They can be any number, and the rest elements will be 0. And this must be a square matrix. So that's why it's called as a diagonal matrix. So let's see the upper triangular matrix and lower triangular matrix. These are two types of triangular matrix. So upper triangular matrix is when the elements above the main diagonal are numeric, and the bottom the bottom triangle are zeros. So in case of lower triangular matrix, we have the same thing, but we will have only the lower triangle elements which is present, and the top elements of the triangle will be 0. This is called lower triangular matrix. And next we have symmetrical matrix. So to understand symmetrical matrix, we need to understand another concept called transpose. Let me write it here. Transpose. So transpose is when we interchange the rows and columns of this matrix. So we just interchange the elements. So instead of writing the elements in row wise, we write it column wise and get a new matrix. It's just like interchanging the elements. So uh, let's say let's take this matrix. So the transpose of this would be, I'm gonna, instead of writing it column wise, I'm gonna write it row wise. So 2 7, so I'm going to interchange the rows and columns. So I'll have 2, instead of writing the 7 in the same row, I'll write it column wise. I'll write 7 here. Similarly, we have 1 and 3. So you see what I did there, I just interchanged the rows and columns. So this is called the transpose of the matrix. So a symmetric matrix is when the matrix is equal to the transpose of the matrix. So even if we change the elements, we will get the same matrix. So in that case, it's called a symmetric matrix. So let's take the example here. So here we have this matrix. So when we write the transpose, we will get the same matrix because these elements are gonna be essentially interchanged while doing the transpose, and diagonal elements would be the same, and these elements are same. So even if we do the transpose, we will get the same symmetrical matrix here. So that's why it's called a symmetrical matrix. So the next type of matrix is orthogonal matrix. So it is a matrix when we take the transpose of the matrix it's equal to the inverse of the matrix. So we will see later what we mean by inverse of the matrix. So let's assume that inverse is like reciprocal of the matrix. So these are the types of matrices. Now let's talk about the basic matrix operation. So for addition and subtraction, let's take these two matrices A and B. So they must have the same dimensions. So they must have the same number of rows and columns in order to perform addition or subtraction. So it's 2 by 2 and 2 by 2. So the way addition or subtraction works is we just gonna do the operation for the corresponding elements like we did in the vectors. So this would be 4, 6, 2, 4. So this would be the resultant matrix. So the general form is if you add A and B matrix, so you'll have the corresponding element at the A and B matrix. So Ij represents the position of the element row 1 matrix, row 1 column of the matrix. So for scalar multiplication with the matrix, it's simple too. You just gonna multiply the scalar value 3 with every of the matrix values, and we will get the new matrix. So 3 into 3 is 9, 3 into 4 is 12, and 3 and 6. So this is how you do multiplication with the scalar. Let's talk about matrix multiplication. So matrix multiplication is not similar to what we did before, which is addition and subtraction matrices. So here we have to ensure one condition, that number of columns in the first matrix must be equal to the number of rows in the second matrix. So here both are equal. So we will check if this case is true. We have like 2 by 2, 2 rows, 2 columns, and 2 by 2 in this matrix. So number of columns in the first matrix means is this number, and number of rows in second matrix is means is this number. So these two must be equal. So if they are equal, then we can perform the multiplication, and the resultant matrix will have the form of the rest two numbers. So resultant form will have 2 by 2 as the result. So let's take another example. We have something like 1 by 3 and 3 by 5 matrix. So here the multiplication is possible because the matrix A has 3 columns and matrix B has 3 rows. These are matching. So what will be the shape of the resultant vector? It will be the rest 2, which is 1 times 5. So it will have 1 row and 5 columns. So that's how this works. So in general, let's say we have matrix A of the shape m and m times n, and we have matrix B which has the shape n times O. So the resultant matrix will have m times O shape. So because the n are matching, that's the first matrix have same number of columns as the second matrix rows, and the resultant matrix will have m times O shape. So let's see how the multiplication works here. So we know what will be the output shape of this multiplication, which is 2 by 2. So it will have 4 elements. So to perform the multiplication, so let's say we gonna find the value of the number in this position. So what is this position? This is 1 comma 1. It's in first row and first column. So in order to find a element of a position 1 comma 1 or I comma j, we need to do the dot product of ith row in the first matrix and jth column in the second matrix. So what's ith row? So we have 1 comma 1. So ith row is the first row in first matrix, which is 1 comma 2, and jth column, first column in the second matrix, which is 5, 7. So we have to do a dot product between these two. So if we do the dot product, we will have this multiplied by this plus this multiplied by this. So what do we have here? 1 into 5 is 5, and this multiplied by this is 2 multiplied by 7. So we will have 19 on the first place. So this also can be imagined as matrix multiplication. So here we see that this 1 comma 2 has a single row and 2 columns. So shape of this is 1 times 2, and this 5 7 is a column matrix. So we have the shape, it has 2 rows and single column, so it's 2 by 1. You can see this number is matching, that it has the same number of columns as the second matrix number of rows. So the resultant matrix will be 1 times 1, so which is nothing but a scalar, a single number. So that's what we get here. We get 19, a single number. So similarly, we will calculate for every position of the element. So let's take the next one. The next one is next position is this position, which is first row and second column. So we have to take the dot product of first row in the first matrix and second column in the second matrix. So this one corresponds to first matrix and this one corresponds to the second matrix. So second column of the second matrix, so this one. So we have to do dot product of these two, so which is 1 2 and 6 8. So we will multiply these two and add them together. So we can just do that directly. So here we just multiply 1 and 6 added by 2 and 8, 2 multiplied by 8, and that will be the element in the position 1 comma 2. So that's what they did here. We got 22, and similarly for the next position is 2 comma 1. So 2 represents to the second row of the first matrix, which is 3 comma 4 3 4, and we have the first column of the second matrix 5 7. So we'll do the cross multiplication or dot product. So we have 3 times 5 and we have 4 times 7, and we add them together and we get these 43, and similarly we get 50, and that's how we do the multiplication. So let's take another example. Here we have a matrix multiplied by a vector. So a vector is nothing but a matrix, but it has only a row or a column here. So the dimensions of this matrix is 2 by 2, and the vector has 2 rows and single column. So the shape is 2 by 1, 2 rows and single column. Do we see the rows and column number are matching? Yes, they are matching. So what will be the resultant vector shape? Which is 2 times 1, so which is the same as this shape. So we have the output of the same shape. So let's do the multiplication. So for the multiplication, we have first position. So for the first position, we have 1 comma 1, so which is nothing but first row and first column. We have only one column here, so we just gonna cross multiply or do the dot product of these two vectors and add them together. 1 into 5 is 5, and we have 2 into 6 is 12, and we will get similarly 39, and that's how we do the multiplication in case of matrix. So let's talk about another type of product called Hadamard product, which is nothing but element-wise multiplication. We're just gonna multiply the corresponding elements. So here we have A matrix A and B. So Hadamard product is denoted by this circle, and we're just gonna multiply the corresponding elements and we'll get the product. So next thing which we're gonna see about is block matrix. So in block matrix, each element of a matrix is also a matrix, which is called as a block. So we have matrix A has elements B, C, D, and E, and all of this B, C, D, and E is also a matrix, which is called as block. So let's say it's 1, 2, 3, 4, and C is something like 5, and so on. You get the point. So this is done to improve readability and computation in case of the block matrices, so that we can structure large matrices efficiently. So we know what a tensor is. Tensor is a generalization of scalars, vectors, or matrices to higher dimensions. So every scalar vector matrix is a form of a tensor. So vector has a single dimension, so it is called 1D tensor. A matrix has 2 dimensions, and that's why it's called 2D tensor, and so on. So the rank is nothing but the number of dimensions a particular tensor has is called as rank. So here the vector has a single dimension, so the rank is 1. And we have the next one is matrix, and the matrix have 2 dimensions, so the rank is 2. And scalar has 0 dimensions, so the matrix is 0. And we have so on. That's how we define the rank. So let's take example of a real life sensor. Let's say we have 100 RGB images with 64 pixels each. 64 pixels each. So what will be the rank of this scenario? So in this scenario, we will have a 4D sensor because we have 100 images and 64 pixels. 64 pixel is in terms of width and height. So we have 64 and 64. And these are colored images, so they will have set of RGB values or channels, just 3 values. So we will have 3 here. So this is called as a 4D sensor in this scenario. And in deep learning, we have frameworks like TensorFlow and PyTorch. So they can handle these tensors as they will keep this as their core structure. So let's talk about vector space. Vector space is a set of vectors along with 2 operations, vector addition and scalar multiplication. And they follow certain rules or axioms which are present here. So vector space, think it of like it's a playground. We have every other vectors, or just a space we have every other vectors, where the vectors can be added or they can be multiplied with the scalar, and they belong to the same vector space itself. So the result of adding and multiplication of the scalar, they themselves belong to the same vector space, and they follow these rules. So these rules we have commutativity. So if we reverse the order of addition, they will be equal. So we have all these rules, they must follow these rules. And the addition of the vectors or multiplication of the scalar must be present in the same vector space itself. So vector space can be anything. It can be arrows or vectors, or it can be matrices, or it can be functions, anything. So let's take example of a vector. So in a 2D plane. So if a vector, we add a vector means, let's say there are 2 vectors. If we add this, we seen before that we'll get a third vector, and the third vector is also in this vector space 2D plane. And if we multiply this vector with the scalar, so it grows in the same direction, it doubles in size. Let's say multiply by 2, it doubles in size. And this vector is also in the same vector space or 2D plane. And it also follows all these other rules. That's why we call this as a vector space. So let's take another example of matrix addition. Let's say 1, 2, 3, 4, 5, 6, 7, 8. And if we add this, we'll also get a matrix of 2 by 2. And we can also multiply this matrix with a scalar, let's say 3, and it will be multiplied to the corresponding elements. And it also follows all these rules, and it's also in a vector space. So let's take another example of a polynomial. So like polynomial, let's say we add two polynomials of degree 3. So we have 2x cubed degree 3 plus we have, let's say, 2x square plus let's say x plus 1, and we have another polynomial x cube, and we have x square, and we just don't have x, so we have 0x, and we have plus 4. So when we add this, we have 3x cube and 3x square and x and 5. So when we add two polynomials with the degree 3, the resultant is also a polynomial of degree 3 or less. So it verifies that it's in a vector space, and it also follows these operations or axioms. So why do I say that the resultant polynomials should also be 3 or less? So here, for example, of instead of x cube, we can have something like minus 2 x cube, and this would be cancelled, and we will not be having this x cube term. We will just be having the x square term, but the degree is reduced. So that's why we say that the order can be equal to or less than 3 or anything in this case. So this also defines the vector space. Also, you can multiply this with any scalar. Let's say 4, we'll just multiply this. So you'll get another vector space. So let's look at another example in NLP, in ChatGPT, and in this AI models. We're gonna be using something called vector embeddings. So vector embeddings are nothing but numerical representation of natural language words. So let's say we have this word king, and we have a word man, and these can be represented by a set of some numbers with machines, so that the machines can understand the meaning, semantic meaning of this word. So let's say king is represented by a set of values like 0.2535 and so on, and man is also like represented by set of values, and these have 300 values or 300 dimensions. So this is a real-time example. So like this high number of dimension is used in AI LLM models to get the vector embedding. So these have 300 dimensions, and these are in a vector space. So there is a famous equation called king minus man plus woman is approximately equal to queen. So logically, this is true. So we have king, we remove man, and we just add the women, we'll get a queen. So if we do this operation in this vector, using these vectors also, like we have some vector representation for women and queen also. So if we substitute the values and we just do this calculation, we can find that the value of it is approximately equal to queen. So why this arithmetic is possible? Because all this vector in this vector space follow these rules. That's why it is called as vector space. So this is another example of vector space, which is used in vector embeddings in large language models. Now let's see linear combination. Linear combination of vectors is a new vector found by multiplying each vector in a set by a scalar or a number, and then adding together to get a new vector altogether. So in put in simple terms, we can just scale a vector and add them or combine them together to get a set of new vectors or a new vector. So let's take these two examples. So we have these two vectors 1 comma 2 and 2 comma 1. So I plotted them here. Let's take another vector 3 comma 3. So we need to get this new vector using linear combination. So we are trying to get a new vector 3, 3 using this linear combination. What does linear combination states? So it states that the vector can be formed by multiplying each vector by a scalar, by an arbitrary scalar, and then combining together to give a new vector. So we have these vectors A and B. So we are multiplying with the scalar. So let's say scalar means any arbitrary value, let's say x and y, and then combining them together. So we're just adding them. So we get a set of new vectors. But in this case, we want this new vector 3, 3. So these are arbitrary scalars, and A and B are the vectors here. So are there any set of vectors which we can multiply and combine them to get this new vector 3, 3? Actually, we don't need the actual value of scalar, so we can just keep it as 1 and 1. So because we can just add them together by itself and to get the new vector 3, 3, you can see here 1 plus 2 is 3 and 2 plus 1 is 3. So just by simply adding them, you will get 3 and 3. So in this case, the scalars is just 1 and 1. So if you see them graphically, you can just add these two vectors, which we saw before. If we add these two vectors, like you can translate this from here to here, you can see the new resultant vector is from tail of the first vector to the head of the second vector, and we got the 3, 3. So this new vector is a linear combination of these two vectors. So let's take another example. Let's say instead of 3, 3, we want another vector. So which is 3, 0, which lies on the x-axis itself. So again, let's write the equation notation. So we have A plus B combination multiplied by arbitrary scalars. We will get new vector, which is linear combination definition. In this case, it's 3, 0. So we can just solve this equation by substituting the values, and we will get the values of the scalars if there's any. So which is, sorry, let me write this neatly, x, y, p. So if we just plug in and solve the equation, we'll get the scalar values as -1 and 2. So if you just multiply the vector A by -1 and multiply the vector B by 2, and if we add them together, we will get the new vector, which is called as linear combination. So we can just try that. So if you multiply this by A, we'll have -1 comma -2, plus multiply this by 2, we have 4 comma 2. So the resultant would be 3 0. So let's see this geographically. So here what we are doing is we just multiply this vector A by -1, which is we are scaling it in the opposite direction. So we are scaling it in the opposite direction. So let me extend the vector A opposite direction. So it's -1 comma -2. It's here. And we are extending vector B in the same direction by scalar value 2, which is multiplying 2, so it just grows in size, doubles in size. So it's here, and if we just add them together, we can see that we'll get this new vector. So we can just translate this vector here. If you translate that, we can see that by adding these two vectors, you will get this new vector. So that's the point. So we can get a new vector by linear combination. Linear combination is just adding together by multiplying each with the arbitrary set of scalars. So let's see, what do you mean by span? So span is nothing but a set of all vectors we can get by the linear combination of a set of vectors. So if let's say we have these two vectors, and the span defines the set of all vectors we can get by linear combination, that is by multiplying the each vector by an arbitrary scalar and combining them together, and the resultant of all vectors we get is this span. So if we think about it, we can get all possible vectors by just combination of these two vectors, linear combination. We can get this vector, we can get this vector, or any vector which is from we can just get every vector from linear combination of these two vectors. So let's see a case where that's not possible. So let's see, let's suppose this vector is on the same line as this vector. So here we have these two vectors. So in this case, we cannot get the combination of other vectors. So the next concept is span. So we saw the linear combination in previous videos. So here span refers to the set of all vectors which we can get by doing linear combination of the two vectors. So let's say we have these two same vectors. So we saw that we can in previous video we can get these vector and this vector by just descaling and adding these two vectors. So if you think about it, we can get any vector in the 2D plane by scaling and adding these vectors. So if you see that this vector A can be scaled all the way from along this line because it can be scaled positive or negative side, and same thing as here, we can scale it all the way. So by this method and adding them together, we can get set of any vectors. So the span of these two vectors is just the set of every vectors in the 2D plane, which is represented by R2. So this is called as span of vectors. So let's say there's a case where we cannot find every vectors by linear combination of the two vectors. So instead of the second vector 2 comma 1, we have a vector on the same line as the first vector. Let's say it's like this. So it's like this, and the value of this vector, it's 2 comma 4. What's here? 2 comma 4. Yeah. So in this case, we can just extend this vector line or scale them only along this axis. So we cannot move to other axis, or let's say other parts of the graph to represent a particular vector, let's say a vector like this or something, because we just can move only on this part. But in previous case, when the vector was like this, we can able to move the vector around by scaling them and adding them together like in the previous case, but in this case we cannot. So the span is not the set of all 2D vectors in this case. So the span of these vectors in this case is just the line. So we can only represent the vectors in this line using linear combination. Let's see about linear dependence and independence. So linear dependence says that one vector in a set can be expressed as linear combination of others, while linear independence means no other vector can be written in the same way. Written in the same way means no other vector can be expressed as linear combination. So we have these three vectors here. So let's take these two vectors alone, which are on the same line. So can these two vectors be expressed as linear combinations of each other? So let's try to express vector A as linear combination of vector C. So the definition says that we can add any two vectors or multiply with the scalar, but here there is only one vector, so we can see if we can multiply anything to get C. Yes, it is just double, it is just scaled 2 times, so we can just multiply 2 to get C. So here we have a condition of linear dependence where uh, this vector just can be scaled to obtain this vector. So also we can see like this vector is a redundant vector, because removing this we are not reducing the span. So the span defines a set of all vectors we can obtain by linear combination, because if we remove this we'll also get all the vectors in the same line, this line, because these two vectors on the same are in the same line, so they are dependent, linearly dependent. So let's see in the case of these two vectors. So we have 1 comma 2 and 2 comma 1. So they are linearly independent, because if we remove this we will reduce the span. If we remove this vector, the span will be only along this line, but this line, this vector, adds another dimension to the span. So it adds another dimension so that we can access all the vectors along this 2D plane with these two lines. But in previous case, we can access only the vectors along this line. So that's what you mean by linearly independent and dependent vectors. So let's see the algebraic way. So algebraic homogeneous equation way. So the linearly independence equation states that if we have the linear combination, they result in a zero vector, and the scalars or the solutions for the equation must be zero. If they are zero, then it's linearly independent. If they are non-zero values, then they are dependent. So what do I mean by this? So let's take these two vectors, and this is 1, 2, which is A, and this is 1, 4. So we are solving these two equations and we are finding if there is any solution which is non-zero. So if we solve this, we have x plus 2y equal to 0, and we have 2x plus 4y equal to 0. So why are we equating to this to 0? Because we equate the linear combination to 0 to check if the vectors can neutralize each other in a meaningful way. A non-zero means in a dependent way. So like in this case, these two vectors, they can be neutralized to 0 because they are in the same line, they can be scaled down. But in this case, these two vectors, they cannot be. So that's why we are solving this equation and equating it to 0 vectors. So if we solve this, we will actually have the solutions as non-zero values, which is 1 and minus 2. So if we substitute these values here, we will get the equation, but sorry, we have minus 2 and 1. So like if we substitute these values here, we will get the equation equated to 0. So these solutions are not 0. That's why they are dependent. But if they are the 0, so 0, if the 0 is like the only solution of this equation, then they are linearly independent. So let's test this with these two vectors. These two, 1. So the equations of these two vectors would be x plus 2y and 2x plus y plus 0. So here you can see like 0 is the only solution here. So that's why they are linearly independent. So let's talk about basis and dimension. What is basis? Basis of a vector space is a set of linearly independent vectors, which is a minimal set, and it spans up the entire space. So what does this mean? They must be linearly independent, which we discussed before, and they must span the entire space. You can form any vector in the space by linear combination of these vectors. So the intuition is like a basis is like a minimal set of building blocks that you can construct any vector in the space without redundancy. So let's take an example of these two vectors, uh, 1 comma 0 and 0 comma 1. So these are called the standard basis vector of R2 in the 2D plane, because these two vectors are linearly independent and they can generate out, they can span every vector in the 2D plane R2. So let's take another example. So here we have the vector 2 comma 1, sorry, 1 comma 2, or we have another vector 3 comma 1. So any vector. So let's check if these two vectors form the basis. So with just these two vectors, we can construct any other vector we seen before. So it spans the entire space of the 2D plane, and they are also linearly independent because they have only one solution, which is 0. So because they intersect, the lines intersect at origin, so they have only one solution, 0, and they don't have any non-zero solutions. So they are linearly independent and they span the entire space. That's why these form the basis of the vector space. And what is dimension? A dimension of a vector space is the number of vectors in the basis for the space. So if the vector space has basis with two vectors, so here for the 2D plane we have two vectors as the basis. So the dimension is just the number of the vectors which make up the basis. So here the dimension is 2. So if a basis has three vectors, so in that case you'll have three axes like a 3D plane. So in that case the dimension would be 3. So all bases of the same vector space have the same number of vectors. So this number is called as dimension. Let's talk about matrix subspaces. Specifically, we're going to see about the overview of column space and rank. So what is a column space? This is the formal definition. Column space of a particular matrix A is the set of all possible linear combinations of its column vectors. So what do we mean by this? Let's take this example of this general equation where we have A is a matrix multiplied by vector X gives vector B. So A is a matrix of size m times n, or m rows and n columns, and X has n entries and vector B has m entries. So when we multiply a matrix with a vector, we will get a new vector. So let's see that with the example. So here we take this matrix as this matrix. I just plotted the columns like this, which is here, and we're going to multiply with the normal vector. So here we multiply it with 2, 1. So if we multiply this, we'll get 4 and 8, which also can be written in this form. So we can take the 2 common and we can represent it as 2 times of the matrix 1 and 2. So let's also take another example, which is we are multiplying the same matrix with the another vector 3 and 2. So if you multiply that, we will get 7 and 14, which also can be written as 2 times 1 and 2. So what is this 1 and 2? It's also in the column of the matrix which we took. So why it is so? So if we see the columns of the matrix, they are linearly dependent, because if we multiply this by 2, we will get this one, which is why I represented it with the same line arrow. So due to that, all the vectors which are spanned by this matrix multiplication only lies in this line. So what do you mean by column space? Remind again, column space is the set of all output or vectors uh, which we get by the product of matrix and this vector. So because the matrix is linearly dependent, that is, they all lie in the same line. So the column space for this matrix will be this line itself, because so let's take another example where the columns are linearly independent. and we just multiply that with the vector, and these are represented in the graph here, and we have this output 5 8. So if we think about it, we can get any vector by multiplying the matrix with a vector, because the columns are linearly independent. And if we extend this line, where unlike in previous scenario where the vector multiplication was just in single line, but here we have two typical axes, so just we can represent any vector as a product. So this is basically just the linear combination of the column vectors which we are calculating. So we're just calculating the different linear combinations. So this is actually called as a column space of this matrix A. So it is also the subspace which is spanned by the columns of A. So the subspace which is spanned by the columns of A in this case is just a whole 2D plane. So that's it about the column space. So let's talk about rank. So rank is nothing but the number of dimensions which the rows of the matrix can extend, or the column space can extend. So it's just a dimension of the column space. So in other words, we can say that uh, the rank is the number of linearly independent columns in the matrix. So in previous case, we just had everything in the single line. So in that case, it doesn't move to the 2D plane. So in that case, the rank is 1. But in this case, we have two lines. So it extends to two dimensions because we have two linearly independent columns in the matrix. That's why the rank in this case is 2. Previously, we saw about column space, which is nothing but a set of linear combination of all its columns. Similarly, there's something called row space, which is nothing but linear combinations of its rows for a particular matrix A. Let's talk about null space and nullity. So, null space, also called kernel of a matrix, is a set of all solution to the homogeneous equation, this one. So we multiply the matrix with any vector and we'll get a zero vector. So it's a set of all input vectors that get mapped to the zero vector by the matrix A. So if you multiply the matrix A with any vector, we'll eventually get mapped to the zero vector. Zero vector is the origin in case of 2D plane. So the vectors which are contribute to this equation, which satisfies this equation, goes into the null space. So this is called null space. And for column space, we have rank, right? So similarly for null space, we have nullity. So the dimensions of the null space is nullity. So it tells how much dimensions does the null space vectors contribute to. So there's also a theorem called rank nullity theorem. Rank nullity theorem, which is a simple equation which says that rank of a matrix A plus nullity of a matrix A gives us the number of columns in matrix A. Let's see what a linear transformation is. It is just a mapping of one vector space to other vector space, often the same vector space, and it follows these two rules. So let's take example of two vector space having set of vectors. Let's say this is v1 and v2, and we have the transformation function itself. So transformation function is nothing but a function which does many things to the vectors, like it can rotate the vector or it can move the vector around in a vector space and so on. So these are mapped to another vector space or the same vector space by doing the transformation, and they follow these two rules, these two important main rules. They say about closure addition and the scalar multiplication. So the vectors, when they are added and did transformation collectively together, which is equal to the individual transformation of the vectors function applied and added together. And the next rule says that when scalar is multiplied with vector and transformation is done, it's equal to the transformation done beforehand to the vector and multiplied with the scalar. So if it follows these two rules and the transformation function maps the vectors from one vector space to another, then it's called a linear transformation. So let's see another perspective using matrices. So let's take the vector x, which is in a vector space or n. So we have the vector x in the vector space Rn. So Rn is the vector space where the components have components are real numbers and have n dimensions. This is mapped to vector space M. So this is the transformed vector. Let's say this is the transformed vector. So transformation is happening here with the transformation function, and this can be represented as a matrix multiplication. So this, when multiplied with the matrix A, which is given here, we will get the transformed vectors for the vector space. So the dimensions of this matrix would be M times N. So that's how we do the linear transformation. Let's talk about the intuition behind linear transformation. So think of linear transformation like reshaping the entire 2D axis system such that all vectors are dragged and repositioned according to a new shape of the space. So if the both input and output vectors during a transformation belong to like the, here we have the input and output vector space. So if they are in the same domain, let's say we have R2, which consists of all vectors in 2D plane. So we have this. So if this is the case, then every vector in the original plane is shifted in a consistent or linear way. So let's see the practical example. So here we have these two blue painted blue vectors. So these are the basis of the vectors in the 2D vector space. So what do you mean by basis? Basis are the vectors which are linearly independent. We have these two, 0, 1 and 1, 0. They are linearly independent, and they can span any other vectors in the vector space. Yes, they can do. And they are the minimal set. That means they cannot be reduced further. Yes, they cannot be reduced further. So we are gonna shift the we are gonna do the we're gonna apply the linear transformation to this 2D vector space. So to apply that, we just gonna multiply this matrix to apply the transformation to each of these vector. So we can see where the new vectors, this basis of the original vector space, is pointing to. So if we multiply these two, we will get A multiplied by E1, we will get as 2, 1. And if we multiply A by E2, we will get 1 and 1. So E1, once pointing to 1 and 0, it's pointing now to where 2 and 1. Similarly, E2, when pointing 0, 1, now it's pointing to 1 and 1. So it's technically transformed. So these are the new like basis vectors for the new vector space, and these dots, this represents the possible vectors which can be present in this vector space. So to understand this, so the matrix A defines what one unit in x direction, which is in the original vector, and one unit in y direction mean like. So it's like before the axis were at 90-degree and unit length, but after transformation the axes are like stretched and slanted depending on where the matrix A sends the basis vectors. So this is how we can think of about linear transformations. Let's talk about types of linear transformation. The first one is rotation. So what do you mean by rotation? Rotation is a linear transformation which turns every vector in a space around the origin by a fixed angle without changing its length. So rotation in short is like spinning all vectors around the origin by a fixed angle. So Here we have the two vectors x comma y. Let me change the color. Yeah, x comma y, which is rotated by the angle of beta to the new location, uh, x bar and y bar. So this is example vector, how it is shifted from a vector space to this vector space by the transformation. So let's see how this transformation happens. So we apply the transformation on this um, vector. So this has the x length of x and y height of y. And let's say the length of this vector, original vector, is r. Okay. So by using the trigonometric formula, we can find the cos of alpha, which is nothing but adjacent side by hypotenuse. So here in the case it's x by r. So we can represent the x in form of r cos alpha. Similarly, we can represent y in the form of r sin alpha. So similarly, for uh, this x dash and y dash, we can apply the same trigonometric formula in this triangle. So in this triangle, the total angle is alpha plus beta. So the total angle is alpha plus beta. So by using the cos formula, what will we have? We will have r cos of alpha plus beta. So similarly for this y dash, we will have r sine alpha plus beta. Now these can be expanded with a trigonometric expressions. So if we expand these two, we will get r sine, sorry, r cos cos beta plus, sorry, minus sine alpha sine beta. So similarly, if we expand this one, we will have r, we'll have r here too. We'll write this in common. Similarly, we'll have r sine alpha cos beta plus cos alpha sine beta. So this is the stuff which we have in final. We can substitute r inside. So we have the value of r cos alpha and r sine alpha. So which we can find it here inside this. If we multiply this and this, we will find r cos alpha and r sine alpha. Similarly, in this equation, we can find r sine alpha and r cos alpha here. You can substitute those values. So if we substitute those values, we will get the final transformed notation. So I will write this here. So the final transform notation here after multiplying the angles would be x cos beta minus y sin beta and x sin beta plus, sorry, I don't have space here. You have y cos beta. So this is the new transform vector notation, x bar and y bar. So we get this by substituting this and this x and y in these equations, two equations. So this is the linear transformation for rotation. So let's talk about the null vector property during linear transformation. So during any linear transformation, the null vector must be preserved. So what do I mean by it? So we have these two properties of additivity and homogeneity, which is the scalar multiplication. So let's say we are doing transformation on a zero vector, and this can be transformation of 0 multiplied by a vector u. So to satisfy the homogeneity property, this can be written as 0 into transformation of u vector, which is the 0 itself because 0 multiplied by anything is 0. So no matter what linear transformation you apply, the 0 vector always remains fixed at 0. So this preservation of origin, so the origin in the case it's t0 comma 0 in the 2D plane, is crucial because it ensures that the transformation maps the vector space onto itself in a way that it respects its structure. So if the 0 vector were moved somewhere else during a transformation, then it would be no longer linear. So let's look at the types of linear transformation. So for linear transformation, they have to follow two rules. So we saw that already. So every linear transformation, including rotation, they must follow the rule of addition and homogeneity. So addition is that we saw that transformation of a vector plus b vector should be the individual transformation added. And similarly, we saw the scalar multiplication of the transformation rule. So let's look at scaling. So scaling is nothing but in every vector in the vector space, the scaling stretches or compresses vector by certain factor along the given axis or direction. So of course they are linear and it changes in length but not the direction unless they are scaled differently in different directions. So let's see what we mean by it. And we can scale it uniformly or non-uniformly. So let's look at uniform scaling example. So every transformation can be represented as multiplication of the vector with the matrix, transformation matrix. So let's say this A is the initial vector, the vector space, and B represents the transformed vector, the vector space. And also remember, every linear transformation, the origin must be preserved. So let's say this A vector is x and y. We have x and y multiplied by the transformation matrix. So here we do uniform transformation scaling. So let's scale it by a factor s. So we're multiplying s. So what will we have? We will have the resultant vector as x, sx, and sy. So it is scaled by a factor x for every vector in the vector space. So s can be any number, like if it's 2, the vectors are double. If it's 0.5, the vectors are shrunk by half. So if you want to scale each axis by a different value, we can do the non-uniform scaling. So instead of single variable s, we have a and b, x and y. So what will we have here? We will have ax and by. So we scale x by a and we scale y by b. So this is the non-uniform scaling. So now we will see the properties of the scaling. So we just saw that it changes length, but it doesn't change direction. So let's talk about projection. So what do you mean by projection? Projection transformation maps a vector into a line or a plane such that the result lies on that subspace. So in this case, the projection maps it on a line. So let's see what do we mean by that. So if we have this a vector, original vector 2, 1, 3, you'll have the x length as 2 and y length as 3. So if we project it with a torchlight from top, what do we see? We just see the length of the vector. This vector will cast a shadow on the x-axis. If we project this on x-axis, we'll see just the length, but we won't see the actual height. Only if we see from the side, we will see the height, but we are not able to see the length. So the projection of this vector on the x-axis, that is the length of the shadow cast by the vector on the x-axis, is just 2. So what will be the transform vector? It will be 2 and 0. So same thing, if you project on the y-axis, we will see 3. So the transformation on a projection on y-axis will be 0 and 3. So that's it, that's projection. So the projection vector is the shadow of the original vector on the subspace. It reduces dimension and destroys information. So yeah, so let's look at this in form of a matrix multiplication for transformation. So you can see the dimension is reduced. So in 2D, the vector is reduced to a line. So but in 3D, we'll have 3 dimensions. So we'll have 3 dimensions. So in that case, the 3D will be reduced to a plane. It will be projected on XY plane or YX plane or ZX plane. So let's look at the matrix multiplication. So let's represent this vector as X and Y. So to project the vector onto X-axis, we can multiply this matrix for transformation. We'll have x and 0, which is just a projection on x-axis. So similarly, we can do that for y-axis. So next, see a reflection. So what do you mean by reflection? Reflection flips the matrix, flips the vector over the line in 2D or a plane in case of 3D, creating a mirror image. So this we have the initial vector. So this is just a mirror image of this vector P. So they have equal angles and they are equal in length too. So it preserves the length and angle, but reverses the orientation. And obviously, this is a linear transformation. It preserves the origin. So let's look at the uh, geometric example. So let's say this is 2 comma 3. So what will we have here? If we reflect this over the x-axis, we'll have 2 and minus 3 because it's negative y-axis. If we reflect this over x-axis, we will have like this. Sorry, if we reflect this over the y-axis, we'll have like this. So what will this be? So this will be minus 2 comma 3, and this will be 2 comma minus 3. So this is just called as the reflection. So let's look at the transformation with matrix multiplication. So to reflect a vector, general vector x, y, or across this x-axis, we will multiply this matrix. X and y, we will get what? X and minus y to reflect this. So this is a simple concept. Similarly, if you reflect a point over the y-axis, we will have plus 1 and minus 1 here, and we'll have the minus here while we're reflecting over the y-axis. So that's it about the linear transformation. So we saw the rotation before. What if we can express the rotation in form of matrix multiplication? Yes, we can do that. So let's say for rotation, there is a matrix, it can be multiplied. So let's say we are rotating this vector in the vector space x comma y by an angle theta. So that can be the rotated vector can be represented as cos theta minus sine theta and sine theta cos theta multiplied by the vector x and y. So if we multiply this, we'll reach the previous derivation which we did before. And yes, let's talk about image and kernel of a linear transformation. So kernel of a transformation T is a set of all input vectors that get mapped to the zero vector. So let's take two vector space and transformation. So we have V and W vectors in the input space. V gets mapped to the vectors in the output space W. So the set of all vectors which get mapped to the zero vector during the transformation contribute to the kernel. So kernel is the set of all input vectors that get mapped to zero vector. It's like the vectors collapse to zero under transformation. In geometric terms, they get flattened to the origin in case of 2D, and it is what part of the input space is lost or destroyed during the transformation. So it is represented by this equation curve T. So let's talk about image image of a transformation T, the set of all possible output vectors. So what do I mean by this? We have two vector space, the transformation. So the image is the set of all vectors in the output space that the transformation actually reaches. So it's the actual output space, but not necessarily the entire output space. So it's just only a subset where the transformation actually sends vectors. So it can be put in a words like it's reachable or produced vectors by the transformation. So let's look at this with the actual transformation example. So for linear transformation, we have the matrix form. This is the transformed vector space vectors. So we have the transformation matrix responsible for transformation and the multiplied by the vector. So let's put it here, T of x equals to transformation matrix multiplied by the vector. So let's take the transformation matrix in this case as 1 2 and 1 2. So this, when we put it in the plane, is just 1 2 this vector, just the same vector twice. So this can be represented by the columns. So when we multiply with any vector, let's say x and y, so what do we get? We get something like x plus y, and in denominator we have 2x and 2y. So if we simplify this, we'll get the form of x plus y and 1 2. So what is kernel? So kernel is a set of all vectors which are mapped to the zero vector. So let's solve that. So during the transformation, they are mapped to zero vector. So let's do that. So let's map this to 0. So x plus y equal to 0. So we have x equal to minus y. So what does this mean? So this means so all the vectors of the form x and minus y after transformation, they go to 0. So that's what we mean by a kernel. So that's why this blue dotted line represents the kernel, because in this line we have x equal to minus y. So that's why this line represents the kernel of the transformation. So similarly, let's look about the image. So for the image, if we see here, we will have the output which we get is always a multiple of 1, 2, because the columns are dependent. So we will have the output only in this line. So image is like the uh, output which we saw, the possible outputs in the subset of the output space which are reachable. So the image represents this whole line. This whole line is just y equal to 2x. So input in matrix term, the output is always multiple of 1 and 2. So it is image of T is just the span of all vectors spanned by one vector 1, 2. So it is in this line, it is spanned by this line. So in 2D it is compressed into a single dimension. So in that process we lost a kernel. So kernel is a set of vectors which get mapped to 0. So the kernel represents the set of all vectors spanned by 1 and -1, which represents x and minus y. So that's what we mean by kernel and image during linear transformation. So let's understand what a determinant actually is. So this is the definition. So let's take an example of the two basis vectors in 2D plane, which is 1, 0 and 0, 1. So what is the area enclosed by it, which is just multiply the sides, which is 1 square units or whatever. So now we're gonna transform this 2D plane by multiplying with the vector, multiplying with the matrix. So the matrix is, let's say it's 2, 0 and 0, 3. So what will we get if we multiply this? You'll get 2x and 2x and 3y. So what happened? The x-axis is scaled 2 times. So this axis, this 1 unit will be now 2 units, and y-axis is scaled by 3 times. So this from the original axis, now this will be 3 times. So 1 unit will represent 3 units here because it's scaled on y-axis 3 times. So previously, these basis vectors will have 1 square unit of area, but now the new vector space, that those vectors will have how much square units of area? We'll have 6 square units of area. Why? We can just multiply the sides of the rectangle, so this forms a rectangle in the new vector space. So 3 into 2 is 6. So the determinant. So now let's understand what is a determinant. So previous we had 1 and now we had 6. So the determinant tells what factor an area enclosed by a set of vectors in a space. So in this case we have basis vectors. So it says what the area enclosed by them scales after the transformation occurs by a transformation matrix. So it says how the area under a set of vectors is scaled by how much or what factor after doing the transformation from one vector space to other vector space. So now the determinant value is 6 because it is scaled by a factor of 6. It is increased by a factor of 6. So it can also be decreased. Also, it can be negative according to the different matrix or different transformations we do. This is just a simple example of just understanding what a determinant is. So in general terms, let's put the transformation matrix as A, B, C, and D. And we are doing transformation on a vector, let's say. So what does A actually mean? So A in the transformation matrix tells us how the axis is being scaled on the x-axis. So we saw the previous case when it was 2, it was 2 times. So similarly, scaling on x-axis, and similarly D represents scaling on y-axis. So what does this B and C represent? Previous case it was 0. So B and C, what it actually represents is B represents the shear in X. Shear in X means like tilting. C represents shear in Y. So B and C represent shear and A and B represent scaling on X and Y axis respectively. So let's understand shear more with an visual example. So let me use this diagram to represent it. So yeah, here we have it. So shear on X represents the shearing along the X. So here we can see the normal square which we formed. So if we share it by H, it becomes like a parallelogram. Like you can see, it becomes tilted by a factor of S. So S is actually B here. So similarly, shearing in case of Y, we have S here. It shears in the Y direction. So it's represented by the C here. And there is no changes along A and D, which is scaling. That's why it's 1. So this is what you mean by shearing actually. And now that we understand shearing, let's see why the determinant is useful. So we have the determinant value. Let's say it's uh, A, B, C, D. So for this matrix, the determinant value is calculated as AD minus BC. Let's understand why it is calculated using this formula. So we are just multiplying these and subtract with these. So let's see why we are doing that. So the determinant value tells a lot of things about the transformation. So if the transformation is negative, it represents that the transformation has changed the orientation. So let's say with the transformation, this square becomes like a parallelogram like this, and because it's negative, it's on the other side. So it's like this, so it becomes negative. The orientation is completely being shifted. So that's what is represented by the negative value of the determinant. Or let's say the determinant value is 0. So in that case, what does this mean? So in that case, we have, let's take this example, 1 2 2 4. So previously we saw that these are linearly dependent. So the vectors lie in the same line, so everything's being squished into the line. So the area which is changed is completely on the line. So that's why if we calculate the determinant by this formula, we have 4 minus 4, which is 0. So that's why this 0 represents that the vector space is squished into the line. So let's also take example of another matrix here. So we have A 0 0 D. So let's write the formula for determinant here. AD minus BC. So when we calculate the determinant, the value would be A and D because B and C is 0. So what does this mean? So A means like scaling on X axis, and D means scaling on Y. Okay, so let me erase this. So if we represent that in the graph below, we'll have like, let's say this is A and this is D. So this is after scaling, we'll have this area. So area formula is nothing but like length into breadth. So that's why we have this A and D. That's where this A and D comes from this equation. So it's just the area of the rectangle after transformation. So let's see about B and C. So let's say instead of 0 here, we have B. So what does B represent? B represents shear in X. So the rectangle, instead of being straight, it becomes tilted like this, as we saw in the diagram. So it becomes tilted like this. So this is basically a parallelogram, right? So parallelogram, what is the area? Area is still base into height, base into the perpendicular height. So the area doesn't change. That's why even when you calculate the determinant, we cross multiply a minus d minus b into 0, which is the same thing, a and d, which is the same area of the parallelogram. So it only like changes if we add also like shear in the y direction. Let's say we have c here. If we have C here, then it will be like AD and BC. This will also shear on the y direction and x direction both. And in that case, this will be the value of the determinant. So in short, the determinant says by what factor the area under a set of vectors in their vector space scales or transforms after the transformation has occurred. So let's talk about inverse of a matrix. Inverse of a matrix denoted by a power minus 1 is another matrix that when multiplied by original matrix A results in an identity matrix. So in simpler terms, it's just the matrix equivalent of finding reciprocal of a number. So what do we mean by this? So identity matrix is nothing but the matrix where main diagonal elements are 1 and rest every element is 0. So let's recall that matrix can be used for transformation, linear transformation. So let's say we transform this vector v and we get transform vector w, and we are using A as a transformation matrix, multiply them with the vector v. So what if we want to get the original vector from the transformed vector? What do we multiply? So in that case, we multiply with the inverse of the matrix, which is required for the transformation from the original vector. So if you multiply these two, we will get the original vector. So let me write in a separate equation. So if we multiply A inverse with the transform vector, we'll get the original vector. So this is the main intuition behind it. So it's basically inverse of a matrix is used to undo the transformation, which is caused by the transformation matrix. So to put it another way, we have this transformation matrix is, so for a series of transformation, it can be represented as multiplication of matrices. So if you multiply this with the inverse of the matrix, so this does the transformation, the rotation, shearing and everything, and this undoes everything. So what will we get? We will get the original vector back, or original matrix back in this case. So because we are doing matrix multiplication, so we'll get just the same thing. So one can be represented as identity matrix. So that's what this equation means. So let's see example of how we can find inverse of the matrix in terms of equations in 2 dimensions. So let's take this matrix A, B, C, T. So the inverse of the matrix is defined by this formula: 1 by AD minus BC, which is nothing but determinant of the matrix, multiplied by D minus B minus C and A. So this is the formula for inverse of a matrix. So let's see how we get this formula. So let's take the example matrix, transformation matrix A equal to A, B, C, D, and let's assume we are looking for the inverse, which is in the form W, X, Y, and Z. So this is the inverse of the matrix which we assume to be. So we have this equation. What equation? If we multiply the matrix and its inverse, we'll get the identity matrix, right? So let's multiply these two. So if we multiply these two, we will get A, B, C, D and W, X, y z, which is equal to what? Identity matrix defined by equation. So if we multiply these two, we will get a w cross multiplication using the matrix multiplication plus by, and here we have ax and bz, and denominator we have cw and dy. Here we have cx and dz equal to the same thing. So here we have set of four equations, four system of equations. So here system of four equations. So this four equations is the LHS and these values are the RHS. So we will have four equations like uh, AW plus BY equal to 1, and similarly for the rest 3. So we have the unknown values which we have to find the inverse of the matrix as WX, Y, Z. So if we actually solve for the WX and Y and Z, it's a long process. So if we quickly jump into the solution, the general solution, which is W, we will get as D by AD minus BC. Similarly for X, we will have minus B by AD minus BC. Similarly for Y, we will have minus C by AD minus BC. Similarly for Z, we will have A by AD minus BC. We can reach this solution by solving the equations using elimination or Cramer's rule. So once that we found the solution, that's it. We can just plug this back into our assumed equation. So if we plug this and take this value out in common, this common denominator AD minus BC will eventually get this equation, and inside that we will have this matrix of the numerator elements. So that's how we derive this formula for inverse of a matrix. So here there's an important point to note. The inverse of the matrix is only possible when the denominator is not 0. That is AD minus BC should not be 0, because if it is 0 then it would be undefined. So because AD minus BC, if AD minus BC equal to 0, the matrix is not vertible. That means it's singular matrix. So what do I mean by it? So let's say we have the original matrix 1 2 2 4. So here the columns are dependent. We saw this example before. So the determinant value will be 0. So if the determinant value will be 0, after the transformation, we saw that every vectors and representations will be squished on a single line. So the 2D will be converted to a single dimension. It squashes the 2D area into a line. So we cannot reverse it using the inverse matrix. So that's why it is not possible when we have the determinant value as 0. So let's understand eigenvalues and eigenvectors. So this is the definition. So you can read it. So let's take an example. So we have the basis vector, the area form under basis vectors in 2D plane. So this is the single unit square area found by the basis vectors 1 0 and 0 1. So let's say we apply transformation to this vector space. So we what basically do is we just uh, apply a transformation. Let's say a transformation matrix A B T 0. So we apply horizontal and vertical scaling, which is shifting, and we apply shear along x. So the output parallelogram looks like this. This is after, let's say, scaling and shifting by some value. So if you see carefully the vector in the original space, this vector, so now this vector becomes this vector. That is, it's not in the same span anymore. Same span represents the vectors which can be represented as linear combinations within itself. So in order to be represented as linear combination or span in this vector, which is the original vector, so this is the new vector which is pointing towards this direction. So in order to be in the same span, they must lie in the same line, right? So this is the line. So they can be either scaled, increased or decreased, but they must lie in the same line. But in this case, it is shifted from here to here. So this is not in the same span anymore after transformation. So let's take another vector example. So in the same transformation, we have a vector like this. So after transformation, the vector direction doesn't change. They remain on the same span. So let's say after transformation, because we don't apply the shearing on y. So after transformation, it just increases by some value, but they all lie in the same line, which is they are in the same span, but they are just scaled by some value. So after and before transformation, these vectors remain in the same span. So this is called a set of vectors, which is called as eigenvectors. So the vectors which doesn't change their span after transformation, they can just be scaled. They can increase or be shrunk by some value, but they don't change the direction, which is they don't change their span. So these vectors are called eigenvectors, and the values in which they are scaled. Now let's say this value is scaled by x amount or just shrunken by y amount after transformation. So the values which they are increased or decreased in the same span after transformation is called as eigenvalues for the eigenvectors. So this is the high level understanding of eigenvalues and eigenvectors. So let's look at the equation for eigenvalues and eigenvectors. So what is eigenvector? When a vector after transformation, it remains on the same span. They just get scaled by a scalar value. Let's assume it has lambda here. Here we apply the transformation matrix A to this vector. So we have a matrix on the left hand side and scalar on the right hand side. Let's assume the matrix has two rows or two columns. So we want to make the scalar into a matrix too in order to make computations easy. So how can we do this? Let's assume this as a linear transformation. Let's assume this lambda as a matrix itself. So it has to be, the vector has to be just scaled by the value lambda, but it should not be shifted from its span. So in that case, we can assume the matrix like this. So when this matrix acts as transformation matrix for the vector x, it just moves around its span. So this is what is represented here. So we just take the lambda common. So we will get this. So instead of the scalar value lambda, we'll have this value. And here we can represent this one as identity matrix. So we have I here. If we move this whole term this side and take the vector x common outside, we will eventually get this equation. So in this equation, if we solve this, we obviously don't want this x vector to be 0 because this is the eigenvector which we need to find. So we can represent this as an example like this. So let's take example the transformation matrix A as a random matrix 1, 2, 3, 4 subtracted by the lambda times identity matrix. So if we do this, we will land here. So this is essentially a linear transformation. So this is the transformation matrix and this is the vectors. So this is a linear transformation itself. So when we do this transformation, it must be 0. What does it mean? So if we do the linear transformation, the determinant of this matrix, transformation matrix, must be 0. Why? Because in this case, we assume that after the transformation, the vector x gets squished to a single line. When it is possible only when the determinant of this transformation matrix is 0. So that's why when we do that, this equation becomes 0. So in that case, we will have this final equation where we have the determinant of a minus lambda I should be equal to 0. So if we do that, we can just cross multiply and equate it to 0, and we will get the values for lambda. So in this case, we will have two values for lambda. Let's say it's x and y. So these values are nothing but the eigenvalues. So if we plug these eigenvalues again in this matrix, transformation matrix, and we can find the set of vectors or the vectors. Let's say represent this vector as x and y. So if we do this calculation for this equation, we can actually find the eigenvectors by substituting the values of x and y, the eigenvalues which we found in this matrix. So we can find two set of eigenvalues and eigenvectors for this system. So that's how we find the eigenvalues and eigenvectors. So the number of eigenvalues is always equal to the size of the square matrix, but the number of independent eigenvectors can differ depending on the type of the transformation which we are implementing. So let's talk about diagonalization. What is diagonalization? So diagonalization refers to the process of transforming a square matrix where rows and columns are equal into a diagonal matrix through similarity transformation. So what does this mean? So let's take a matrix A, which is responsible for linear transformation. So it rotates, skews, or shifts the vectors in the vector space. Let's say it rotates a vector from this side to this side. So here, let's see the idea of diagonalization. The diagonalization changes your point of view. Changes your point of view. So what do we mean by this? So instead of applying the transformation directly in the standard XY or XYZ plane in case of 3D, so instead of applying this in the coordinate system, it just switches the basis to a new basis. So what do we mean by it? So here we have the basis in the coordinate system. What is the basis in the coordinate system? Which are these two vectors, 1 0 and 0 1. So with these vectors we can span any other vectors. So it just changes the basis completely to a new basis. So let's say the new basis, and it is a smarter one. Let's say this is the new basis instead of that one, and this is a smarter one. Why is this called a smarter one? Because here the linear transformation, which is caused by the matrix A. So let's say in the original case it's a rotation, so which is complex, but in the new system of basis, this rotation just becomes a linear scaling. So you don't have to do the complex transformation, it just becomes scaling. So that's why this is called a smarter set of bases, and this process is called diagonalization. So let's see how this actually works. So let's take matrix A. This one has eigenvectors. Eigenvectors are the vectors which doesn't change their span after transformation. So let's say these are the vectors, and we have eigenvalues lambda 1, lambda 2, up to lambda n. So these eigenvectors form a new coordinate system which is called as new basis. So in that system, A behaves simply. What do we mean by that? So instead of rotating or skewing such complex transformations, it just stretches or compresses along each eigenvector. So that's what diagonal matrix does. We know diagonal matrix, right? Only diagonal elements are present, x, y, z. So by applying this transformation to a vector, it just scales the vector along x, y, and z direction respectively. That's it. So that's what it does here. So if you take this in a form of equation, this is what we get here. So this is a matrix, can be represented as a diagonal form, like a diagonalization. So here we have P, D, P. So what do we mean by PDP? So let me erase this. So D is the diagonalization diagonal matrix, and so the diagonal matrix will have the eigenvalues. So you will have let's say represent eigenvalue lambda 1 and lambda 2. So this is a diagonal matrix, and here P is just a matrix whose columns are eigenvectors, whose columns are eigenvectors, and P inverse is just the inverse of the matrix P. So if a matrix can be represented as this form, and it is diagonalizable. So uh, let's see the intuition behind it. So what we do here is basically shift the basis of the system with this matrix along the eigenvectors, because eigenvectors just span when the transformation is applied with the matrix. So we just shift the basis and we just do the scaling with the diagonalization diagonal vector here, which is just the eigenvalues. So it's just scaling of the eigenvalues, which we saw before, and we again shift the basis back so that we can do complex operations just by shifting the basis, or we can say it as diagonalization. So this is useful in various cases. So we can see this can be used in cases where you want to raise a matrix to higher power. So you just don't have to multiply the matrix 3 times, but you can use diagonalization to accomplish them. Also, it is used in matrix multiplications. So how can we achieve this? Let's say we want a cube or a power 10. So in that case, what you have to do is we just have to find the eigenvalue, let's say EV, which is lambda 1 and lambda 2, and in this case, so we have eigenvectors, let's say v1 and v2. So if we find that, instead of the diagonal matrix, we can represent it as a eigenvalue diagonal matrix, and we can find this P matrix, which is nothing but the columns are eigenvalues, and similarly we can find it inverse, and we can represent and check its diagonalization. So how does this work? So if we want a power 10, this right side equation will be PD P power 10. So we'll have 10 times the same equation. So we'll have this PD P minus 1 multiplied by PD P minus 1, and so on to 10 times. But we can see that this transformation P, matrix P and matrix P inverse just cancels out. So what will we have here is just the D. So we will have 10 D's between them. So we'll have P D power 10 and P inverse. So D power 10 is actually easy to calculate, because if we have a diagonal matrix x, y, we just have to increase the power of the diagonal component to get the corresponding diagonal matrix. So with this, easily we can find a power 10 or a power 100 or so on. So generally we have a power k equal to p d power k p inverse. So this is the intuition behind diagonalization.
Let's look at singular value decomposition. So it is like generalization of diagonalization, because diagonalization works only for like square matrices, but SPD can be used in any kind of matrices, both square matrices and non-square matrices like rectangular matrices. So singular value decomposition rewrites any matrix as combinations of rotations and scaling, helping us to analyze, simplify, or compress it. So to put it in a simple way, we can represent any matrix transformation as product of these three matrices. So before looking into this, let's understand some concepts. Let's understand the power of rectangular matrix. So rectangular matrix is any matrix which doesn't have same number of rows and columns. So it's like a rectangle. So we have 1, 2, 3, 4, 5, 6. We multiply this with the vector, say 1, 2, 3. This has 3 dimensions. we have 2 rows and 3 columns. Here we have 3 rows and single column. If you multiply this, the output will be of the shape 2 by 1. So it will have x and y. 2 rows and single column. You saw that the vector in 3 dimension is converted into 2 dimension. So a dimension has been reduced. So similarly, you can also add dimensions. So let's put the rectangular matrix in this way: 3, 4, 5, 6. And if we multiply this with the vector 1, 2, 3 rows and 2 columns, 2 rows and single column, we multiply this vector will be having another dimension because it will be having 3 rows and single column shape. So the rectangular matrix can be used to add or remove dimensions. So now that we understand the power of rectangular matrix, let's see a power of symmetric matrix. Symmetric matrix, you know what is symmetric matrix. So on the either side of the diagonal, the values must be same. So why do we need the symmetric matrix? So the eigenvectors which is formed, which we calculate from the symmetric matrix, they will be orthogonal or perpendicular. Why do we need them to be perpendicular? So let's say these are the eigenvectors which we found and they are perpendicular. The green line are the eigenvectors or orthogonal vectors. They are perpendicular. So this pair of orthogonal vectors can be used to form what is called as orthonormal basis. So the vectors, because they are perpendicular to each other, they are independent and non-redundant. What do I mean by this? They act like a rotation or reflection operators. So they form like an orthogonal basis, which is like basis. You know what is basis? Is like another set of like axis system. So which is formed by the set of vectors. So let's say in 3D, these are the axis x, y, z. You have a shape of sphere or ball. So let's say this dotted lines represent the orthonormal basis, which is formed by orthogonal vectors. So if we rotate this on the orthonormal basis or reflection, or if we do any operation, they will preserve the length and angles, which means that they will appear the same. They will not increase in size or disorient the shape or uh, just distort the shape or something, but they will be just the same. It's like just rotating and viewing a 3D object, that's it. So which we can easily do with this orthonormal basis, which is formed by orthogonal vectors. So orthogonal vectors is like eigenvectors formed by the symmetric matrix. So that's why we need the symmetric matrix. So now that we understand the power of symmetric matrix too, let's understand how we can get symmetric matrix from any matrix. So let's say we have this rectangular matrix. I want to convert this into symmetric matrix. So the simple thing here is we just have to multiply it with this transpose. Let's say this matrix is A, multiply with the transpose 1, 4, 2, 5, 3, 6. So the output will be a 2. This will have 2 rows and 3 columns, and this has 3 rows and 2 columns. So the output will be a 2 by 2 matrix, and you can check that the matrix will be symmetrical. Similarly, you can find another symmetric matrix by just reversing this multiplication. If you multiply A transpose in A, we will have the output with 3 rows and 3 columns, which will also be a symmetric matrix. So we can find 2 symmetric matrices. So now that we also understand how we can get symmetric matrix from any matrix, next let's go to this part. This part, the A transpose A, is called as right part in the context of SPD, and this part is called as left part. So this is here related to the equation, which we will see later, related to the components of the equation. So the Eigenvectors which we get from this right part are called right singular vectors, and the eigenvectors which we find from the left part is called as left singular vectors. And the eigenvalues which we find for this either left or right part, they will be the same actually. Why? Because if you find the eigenvectors for this or this, they are intrinsic to the A itself. So one may have another extra zero while calculating the eigenvalues, but the non-zero values of the eigenvalues of these both two, they will be same. So we have the eigenvalues, and the eigenvalues will be like squared because we are actually multiplying the transformation matrix with this transpose. So they'll be having the square effect. So in order to get the actual translation value, like how are they stretched or moved along the axis, we need to actually take the square root of eigenvalue so that we can get the actual magnitude of those effects. So the square root of the eigenvalue is what we refer to as singular values. So now that we know every concept, let's dive into the step and conceptual flow. So let's understand this with an example. So here we have the transformation matrix A with the shape 2 by 3. So what the transformation is responsible for is it converts a 3D object into 2D. So this is the U matrix and sigma and V transpose. So U matrix is nothing but a matrix whose columns are the left singular vectors, and V transpose have the columns as the right singular vectors, but they will be taken transpose. So when we come to sigma is nothing but a rectangular matrix. They'll have the same dimensions as the input. In this case, it's rectangular. And the diagonal will be the singular values, which is square root of the eigenvalue. So let's represent it with sigma. So this is what the components of this equation represent. So let's take an example. So as I said, this converts 3D into 2D. So let's take a shape of an ellipsoid. Ellipsoid is like 3D form of an ellipse, like an egg. So the first step is this one, rotate input, which is done by this component V transpose. So how is it rotated? It is rotated along the direction of the orthonormal basis, which is extracted from this V transpose of V. So we have let's say this is the orthonormal basis, and this ellipsoid is rotated along the orthonormal basis. So why do we do it? Because the shape stays the same, it's just reoriented, that's it. So why do we take the transpose? If we take the transpose, just the shape gets uh, different oriented, but the axis remains the same. But if we just didn't do the transpose, the standard basis itself will get reoriented. So that's what the importance of transpose here means. So after that step, let's look at the next step, which is stretching in new directions, which is achieved by this component sigma. So now that we have the shifted ellipsoid, we have this sigma. It is responsible for stretching and shrinking. It's a rectangular matrix. So remember, this rectangular matrix can be used to add or remove dimensions. In this case, it's removing a dimension, so this 3D becomes 2D. So this ellipsoid becomes a stretched 2D flattened ellipsoid, and it is stretched. Why? So this is the normal rectangular matrix which is responsible for squashing it along the axis from 3D to 2D. So now we have 2D 2D ellipse, and also it needs to be stretched, right? Because it has to have the effect of the singular values, which is square root of the eigenvalues, so that we can actually scale it. So that's why these values come in. So this can be used to stretch and get the actual like magnitude of the shape. So after that is done, we go to the next step, which is rotation or reflection of the result into the output space. So which is done by this component U, this matrix. So this has the left singular vectors. So what it does is it rotates the 2D to the output space of the 2D ellipse. So notice that we are not taking transpose here. So it just shifts the standard basis to align with this new new transformed shape. So that's it. That's the conceptual flow. So SPD generally means that we can represent any transformation matrix in this form. And if you see the mathematical steps, so we have in this equation, first we need to have the input A here, and after that we'll find the A transpose A and A transpose in order to get the symmetrical matrices. And after that we will find the eigenvalues and eigenvectors. Eigenvectors are for each matrix, and eigenvalues you can find for one, and after that we find the sigma matrix, which is just the diagonal values where the eigenvalues and eigenvalues and its square root is present there, which is nothing but singular values. So after that we will form the right singular vectors, the matrix V, and we'll take its transpose, and after that we'll find the left singular vectors and find the matrix U, and by using all of this we can reconstruct the original matrix A. Let's talk about pseudo-inverse. A pseudo-inverse is a generalization of inverse that works even when A is not square or invertible. So to take inverse, we have two conditions. That is, the matrix must be a square matrix and it must be invertible, which is the determinant must not be zero. A pseudo-inverse enables us to find the inverse even if these cases are not satisfied. So it is denoted by this symbol plus for matrix A. This is the pseudo-inverse. So why do we need to calculate the pseudo inverse? So it is useful in solving system of equations where you have two cases, which is underdetermined system and overdetermined system. So underdetermined system is in the system of equations we have more number of variables than we have for the equations. Let's say x plus y equal to 5 or something, some set of equations. We have more number of variables than equations, and overdetermined is the opposite. So we have more number of equations than the variables. This is common in machine learning, and also it is used to find the best fit solutions where the solution does not even exist. So we can find the best fit solution in case of those equations. So let's say we have this equation which is in matrix form AXB, and there is no exact solution for this. So this can be rewritten as x equal to A, which is pseudo inverse of matrix AB. So if we just find this, we can find the approximate solutions and then we can multiply with B. So let's see how we can find A plus pseudo inverse. So we can actually find this from SVD. So this is the SVD. So here we can just use the V, which is the uh, matrix with columns which consist of the right singular vectors, and this is the U transpose. So U consists of the matrix with left singular vectors, and E, which is sigma. So sigma star plus here, it's the same sigma, but we take the reciprocal of the non-zero singular values in this sigma matrix, and we take the transpose of the matrix. So by doing that, we get this sigma plus. So what conceptually happens here is we rotate back to the diagonal basis, which is given by this U transpose, and this sigma plus helps it to scale backwards. So here sigma uses it to scale forward. So it's like backward process. So it helps to scale backward, and this V rotates back to the original input basis. So by doing this, we can find the pseudo inverse and we can find the best fit solutions. So now that we understand how to represent and manipulate data in form of vectors, matrices, and transformations, let's move on to learning about solving system of linear equations. So in machine learning and data science, we often come across this. So it's useful for various purposes, like when we are optimizing a model or reducing a loss function. So linear algebra. So let's say we take these two equations. So we all know that we just need to find the values of x and y such that they satisfy these two equations. So this also can be represented in form of a matrix Ax equal to B. A is the matrix of the coefficients of the variables, and X is the variable vector which just has the variable values, and B is the output vector which just has the output values. So you already know that when solving this system of equations, we get into three types of solutions. So first one is unique solution, no solution, and infinite solution. So let's talk about unique solutions. So in 2D view, you already know that when the equations, when they're represented in form of a line, so if they intersect at a point, they have a unique solutions. So this point xy, let's say xy pair that satisfy the both equation is the only point. So if you represent this in form of a matrix, you will have A. Let's say this is the matrix A. So the condition for unique solution is that the matrix A must be invertible. Invertible means the determinant must be not zero, must not be zero. The determinant must not be zero. So this implies that the rows are linearly independent. The rows of the matrix A are linearly independent, so they can span the full 2D space, and we get the unique solution. So why do we look at the rows of the equation and not the columns? It's pretty obvious. So each row represents an equation in this coefficient matrix. So the row dependence tells us that if the system is consistent and solvable. So if the system is consistent means they have a solution. Inconsistent means they don't have a solution. Now let's look at the next type of solutions which we can achieve. No solutions. So you know the geometrical view when we represent the equation in form of line, they are just parallel and they don't meet each other. So that's why we don't have any solutions and the system is called inconsistent. So let's take the matrix form. This is the matrix A. So if they don't have any solutions, the rows of the matrix A are linearly dependent, means they are pointing in the same direction, right? But the output vector B does not lie in the column space of A. So what does this mean? So why are we checking if B is in the column space of A? Because we see the equation AX equal to B. So it's a kind of linear transformation which we can assume. So we can express vector B as linear combinations of columns of vector A if this is equal. So if we cannot prove that the B output vector is in the column space of A, it means the system of equation doesn't have any solution, and that's why the system is inconsistent. So let's look at the next type, infinite solutions. So infinite solutions means geometrically the lines just overlap each other. They just overlap each other. So we can see that they intersect at every point on the line. So the system has infinitely many solutions. So let's look at the matrix view. We have the matrix A. So the rows of the matrix are linearly dependent. Yes, they're linearly dependent. And B output vector also lies in the column space of A. That's why we have infinite solutions. So the system is consistent, but there is not a unique solution. So there's a whole line or plane in case of higher dimension like 3D of solutions. So now that we understand the system of linear equation, there are many methods to solve them, many decomposition methods to solve to find the solutions in matrix form, even in this form, which you know already. So those are too computational and math heavy. I'm not going to be going into that. So this is it for the linear algebra basics for data science and machine learning. Thank you for watching.